What's up, boys and girls and everyone else? Welcome again to another science video lesson episode. In this video lesson, we will going to talk about word problems. Yes, we will going to talk about word problems and we will going to solve them using the mirror and lens equation. So, how to do that one? So, stay a while and listen guys as I discuss that one today in our science video lesson. So, let's go to the video lesson. Alright, so we are now right here in our video lesson for this episode. Alright, so we have here the mirror and lens equation, a quantitative analysis. Okay, so mirror equation, word problems, and lens equation, word problems. So what are we going to do here? Alright, so we will going to use math. Okay, we will going to use math in solving these word problems related to spherical mirror and lenses. Okay, so last time we discussed what is the ray diagram all about, and also we derived the equation coming from that ray diagram. Okay, so in this video lesson that we have right here, so we will going to solve it quantitatively. Okay, so those word problems. So let's go. Okay, so we all know how to draw a ray diagram. So starting with the concave mirror that we have right here, we draw the principal axis, okay, and something like a tangent line over here, okay, tangent line to the mirror. And we have the 2 points. So we have here the center of curvature and the focal point. Okay, so we have here the center of curvature and the focal point, and here is our object. Okay, so now to start our ray diagram, we have the first ray that we have right there. We called it principal ray that goes parallel to the principal axis, then going to the focal point like so. And the next one is a focal ray. The focal ray is something like goes to the focal point and down to the parallel to the principal axis, like the one that you see there. Okay, so, and we draw the image something like this. Okay, now, the question is, what is the limitation of our ray diagram? Okay, so if you want to answer that question, just put it in the comment section below. So by the way guys, if you don't have any idea about what is this ray diagram all about, so just click the link above. Just click the link above for my video lesson about this ray diagram that we have right here. Okay, so what are the limitations of your ray diagram? Okay, so the first limitation of your ray diagram is that you need, all right, to make an accurate, all right, so to make an accurate prediction of the image that we will form right here, to make an accurate prediction, you need your drawings to be precise. Okay? What do we mean by that? So it means that you need your lines that you have right here. Your lines should be straight enough, okay? Straight enough and precise enough to make the image, the height and the distance of the image to the mirror, make it more accurate somehow. Okay, so it depends upon your illustration at the end of the day. So if your illustration for the ray diagram is not that good, so therefore it will affect how you measure the image and also the distance of the image through the mirror. So it will affect, overall it will affect that one. So that is the limitation of your ray diagram. And also, the ray diagram is very tedious, okay? It's a very tedious work. Okay, it is a very tedious work because it requires a lot of time for you to draw these lines that you have right here. Okay, so don't forget to follow the law of reflection and the refraction for lenses, something like that. Okay, so with that, my question is there any other way? Is there any other way to predict the characteristics of image besides the ray diagram? Okay, so with that, okay, in our previous lesson, we have the qualitative. So for today, we can say that it is yes, that there is a way to predict the image characteristic using or besides the ray diagram that we usually use. That is by math. Okay, yes, you heard it right. It is in form of math. Okay, so we will use numbers to accurately predict the image characteristic. Okay, so rather than using ray diagram, we will use math with this one. Okay, so let's take a look. Alright, so this is our mirror equation. Okay, that we have derived last in the previous video lesson. Okay, so that was the ray diagram, and there is one way. Alright, so there is one way to use the mirror equation to calculate the position and size of the image. Okay, so there is one way. Okay, there is one way to use that one. Okay, to calculate this image that we have right here, or to predict the image that you have right here, we need to use the following formula. So we have the magnification formula and we have the mirror formula over there. Okay, so now if you want to know where does this formula came from, so you can watch the link, okay, on the video lesson above this video. So it's right there. Okay, it's right there. So just click the link from that, and you can you will see where does this equation came from. Okay, so that is our mirror equation. So to start with, let's take a look at this problem. Okay, so assume that a certain concave spherical mirror has a focal length of 10 cm. Okay, locate the image for an object distance of 25 cm and describe the image characteristic. So how can we describe the image characteristic? Alright, so how can we describe the image characteristic for this one using numbers? Okay, so we have here the mirror equation. We have here the mirror formula. And we substituted all of these values that you have right here. And upon solving this one, we get 16.67. Alright, so we get 16.67. Now, what does this number means? Okay, so what does this number means? It means that the image is a real image because it is positive. Alright, so we have here the positive distance of the image, that is a real image. And not only that, we can also locate the image, okay, using this answer that we have right here. Okay, so how do we locate this one? So the focal length was 10 centimeter. So its center of curvature, alright, so its center of curvature is 20 cm. So remember, 10 times 2 is the center of curvature. Okay, focal length times 2 is the center of curvature. So we have here the 20 centimeter. So what does it mean? It means that the distance of the image over there is in between these two. Okay, so it is in between these two that you have right here. So it means that the location of the image is between center of curvature and F. Okay, it is between center of curvature and F. So in this case, guys, everyone, so we locate. Okay, so we try to find out that the type of the image that was produced here is a real image, and the location of the image is between C and F. Now, how about the size and orientation of the image? Alright, so how about the size and orientation? But before we go to the size and orientation of the image, let's take a look at some conventions that we have right here. Okay, so you should remember this convention before you start working on some word problems related to mirror and lenses. Okay, so starting first with the distance of the object and height of the object. Alright, so the height and distance of the object are always positive. Why they are always positive? Because this one is for your reference. Okay? So this one is for your reference. So there's no such thing as negative distance. And also there's no such thing as a negative height. Okay? So this is the real thing that we have right here. This is the real thing. Okay? So that is why it is always positive. They do not have a negative version. Okay, next one. How about the distance of the image? Okay, so first one, if it is a real image, then therefore it is positive. Then we have it virtual. Okay, so we have it virtual if it is negative. Okay, so what is the reason behind this one? So the real image, as from its definition, from its definition, real images are images that is formed on the same side as the object. These are images that are formed on the same side relative to the object. So, it means that same side. So, if the object is positive, then therefore the image is also positive because they are formed on the same side. Okay? They are on the same side. The image is on the same side. Then therefore, if virtual is opposite, if the virtual image is formed in the opposite side, then therefore this is a negative version. Okay? So this is a negative. So that was for the distance of the image. Now how about the height of the image? Now the height of the image follows the cosine convention on the Cartesian plane. Alright, so remember the Cartesian plane. So this is positive, this is negative, this is negative, this is positive. Alright, so it means that if it is upright, it goes up there. So the object or the image is upright, then therefore that is positive. So as in the Cartesian plane, this one. Now if the image is inverted, then it is something like here. So that will be negative. Okay, next one. How about the concave and convex mirror? Alright, so the focal length, okay, in terms of focal length, in a concave mirror, it is positive, and in the convex mirror, it is negative. Why? It's because one thing, the image that was formed in a concave mirror are real images. Then therefore, it is on the same side as the object. So therefore, the concave mirror can be positive because the image that was formed on this case is on the same side relative to the object. So if the object is positive, then therefore, the focal length is also positive. Okay? Next, since this one, the convex mirror is forming the image opposite. Okay? It is opposite to its position of the object. So therefore, we can say that it has a negative convention, negative sign convention, because of having a virtual, okay, because of having a virtual kind of image. Okay, so that was the convex. And also in terms of their opening, all right, so the concave mirror, the reflective side is on this side, so therefore the focal length is on the same side as the reflective side. Okay, now the convex mirror is the reflective side is on the opposite side. So therefore, the focal length is located opposite to the reflective side. Okay, so opposite to the reflective side. So the focal length is over here. So it means that it is negative sign convention. Okay, so next one. In terms of magnification. So we will follow. Okay, so we will follow what is on the height of the image. Okay? So, if it is upright, it is virtual. Okay? So, upright image or positive magnification means an upright image. Like so. Okay, so that is positive. Okay, and an inverted image means negative magnification. So, positive M, this one is negative M. Because it follows the height of the image, which is inverted. Like the one that you have right here. Okay, so these are the sign conventions that you need to remember and you need to take note before you solve any word problems related to lens and mirror. Okay, so let's go to the magnification equation. Now, in order to calculate the orientation and size of the image, we need to use the magnification equation, and it is right here. Okay, it is right here. Okay, so it is said that magnification is equal to the ratio of the distance of the image over the distance of the object. And also, magnification is also the ratio of height of the image and height of the object. Now, remember the answer that we had earlier is 16.67. So if we plug it right here in our equation, so we can get 16.67 divided by the distance of the object, which is 25. Okay, so we can get 0.67x. Now, the unit for magnification is x. Alright, so x means that is a factor. Okay, so that is a factor. So, what is this negative and this number all about? Okay, so the first one, the negative sign. The negative sign means that it is a negative magnification. It is inverted. Alright, so it means that the image is inverted. Next one, how about the number? How about the number that we have right here? So, the baseline is 1. Alright, so this is the baseline. So, if the number is less than 1, like the one that we have right here, 0.67, then the image is reduced. Okay? Next, if the number is greater than 1, like the one that we have right here, the image is enlarged. Okay, so the image that we have right here is enlarged. Okay, so that was the number that we have right here. So in this case, is the image reduced, enlarged, or even if it is equal to 1, therefore it is the same size. So what is the size of the image in our problem, in our previous problem that we have? So the image was reduced. Okay. So, it is located between C and F. The orientation is inverted. The size is reduced. And lastly, we have the type of image is a real image. Okay, so that was the magnification equation. So, let's put that one to good use. Alright, so let's assume that a certain concave spherical mirror has a focal length of 10 cm. Locate the image for an object distance of 5 cm and describe the image's characteristic. Okay, so I already plotted it right here. You can pause the video. Alright, so you can pause the video for you to find for you to try to solve this problem. And let's see if you will arrive on the same, if you will arrive with my answer if it is the same. Okay, so upon computing or upon solving this one out, you will get negative 10 centimeter. Okay, you will get negative 10 centimeter, and that negative 10 and this negative 10 centimeter will be plugged right here. Okay, will be plugged right here on the magnification equation. So, solving this one will get you, okay, will give you 2x magnification. So, it means that we have 2x magnification, and that is positive due to the fact that you will cancel the negative. Alright, so you will cancel the negative signs there. So what does this mean? Okay, what does this mean? The image is virtual, opposite side. The image is enlarged. Okay, because it is greater than 1. Alright, so the image is enlarged. The image is upright. It's because this one is positive. Alright, so the answer for magnification is positive. Okay, so, and lastly, that is virtual. It's because we have negative 10 distance of the image. The negative sign that you have right here, the negative sign, that tells us that is a virtual image. Now, what is the location of the image? What is the location? So, since that is virtual, we can say that it is behind the mirror, even though there's no such thing as behind the mirror. Alright, so the image seems to be behind the mirror. Okay, that is the location of your image. Alright, so with that, let's go now to our sample problems related to mirror and magnification equation. So here we are in our sample problems for mirror equations and magnification equation. Alright, so let's start first with this problem that you have right here. Okay, so a light bulb is in front of a concave mirror which has a focal length of 4.69 centimeter. Alright, so what do we have right here? Okay, so what do we have right here? So, okay, the real image is located 9.2 cm from the mirror and determine the distance of the original object from the mirror. So, let's try to see what are in this problem. So the first one, the problem is, the first thing that you need to do on the problem is find more concepts. Okay, find more concepts that will help you in solving the problem. So number one, the problem said that it is using a concave mirror. Alright, it is using a concave mirror. And also, the real image was formed at the end of the day. Okay, so the image was formed at the end of the day. So these are the two things that we should take note of. Okay, when we are going to solve any word problem related to mirror and lens equation. All right, so number one. Okay, let's start writing now the given data. So the focal length was 4.69 cm. All right, so the real image. All right, so over here. So the real image. So this will be treated. So 9.2 will be treated as distance of the image. So that will be 9.2 cm. And finally, we are asked to find out the distance of the original object. Alright, so that is the distance of the original object. Now, before we continue the process, okay, let's check first if our data is correct. Okay, now the real image was formed, so that was the distance of the image. Okay, so did we forget some sign? Okay, so did we forget some sign here? I think we did not forget anything. Alright, so we do not forget anything here. It is correct. So remember that positive distance of the image means real image. Alright, positive distance of the image means real image. So how about the focal length? Alright, so the focal length is positive, which is also correct because it is a concave mirror. Remember, concave mirror are positive, convex mirror are negative. Okay, so that is the thing here. So we can now solve for this one. Okay, so the formula that we were going to use here is the mirror formula. Okay, so that was 1 over f is equal to 1 over d sub o plus 1 over d sub I. So there's a mnemonic over here. You can use if. Alright, if I do, I die. Alright, so if I do, I die. Okay, so like this. Okay, so for you not to forget this formula. Okay, so let's substitute all the values that we have right here. So we have 4.69 is equal to 1 over 9.2 plus 1 over d sub o. There you go. Now in this case, we were going to use least common denominator or least common multiple. Okay, so we have right here the 9.2 d sub o. Okay, so that is the 9.2 d sub o. Then we can proceed now. Okay, so 9.2 divided by 4.69 over 4.69. Okay, so we have right here 1.961. All right, d sub o. Okay, so again, you can pause this video if you want. Okay, so for you to try to answer first. Okay, so next one is d sub o because it will cancel the 9.2. And lastly, we have plus 9.2. So there you go. So with the bit of algebra, okay, so with the bit of algebra right here, so we can transpose this one over here, okay, to get negative d sub o plus 1.961 d sub o is equal to 9.2. So in this case, we get d sub o minus 1 plus 1.961. So that will be d sub o 9, rather I have already the d sub o. Alright, so that will be, okay, 0.961. Alright, so 0.961, 9.2. So the d sub o will be, okay, 9.2 over 0.961. So the answer is 9.57 centimeter. Okay, what is the complete answer? So the complete answer is the distance of the original object from the mirror is 9.57 centimeter. Okay, so what does this one means? What does this answer means? Where is the object located? Where's the object located in the first place? Now, if you're going to take a look at the focal point, alright, so if you're going to take a look at the focal length is 4.69. Now, if you double this one, you will get the center of curvature, which is 9.38. So, which you can get 9.38. So, in this case, guys, 9.38 centimeter, it tells us that the distance of the object is beyond C. Okay, is greater than C. Okay, so the distance of the object is greater than C that we have right here. Okay, so that we have over here. So if we will draw this one, so this is now your principal axis. We have your focal point and we have your center of curvature. So the object is located here. And let's see if that will be an inverted image. Alright, so basically that is an inverted image. Alright, so that is our first sample problem about mirror equation. Okay, let's try to solve another one. Okay, so you can pause this one if you want to answer. Okay, so a candle is placed a distance of 16.58 centimeter from a convex mirror. The virtual image was formed 12.89 centimeter from the mirror. What is the focal length of the mirror? Okay, so let's take a look at the problem. The mirror that was used is a convex mirror. Alright, so the mirror that was used here is a convex mirror. So there is a virtual image on the problem. Okay, now the problem is looking for the focal length. Okay, so in order to solve this one, we should write the data that we have right here. Now, what is this 16.58? This is the distance of the object. Now, you don't worry about the distance of the object because it is always positive. 16.58 cm. Alright, next one. The virtual image. So this is a distance of the image. Okay, since that is a virtual image, based on our sign convention, a virtual image is a negative sign. Alright? Contains a negative sign. So therefore, that will be 12.89 cm. Then, we have the focal length. Okay, so then we have the focal length, which is, that is missing. Okay, so let's check our data if we are good and ready to go. So, all the signs are here. Okay, especially the D sub I. Okay, especially the D sub I. This negative sign is very important. Okay, this negative sign is very important because if you don't have negative sign here, it will affect your final answer. Okay, so in this case, we will use if I die, if I do, I die. Alright, so substitute the numbers that we have right there. So 1 over F is equal to 1 over 16.58 plus 1 over negative 12.89. Right, so as you can see, I didn't write the units, okay, to conserve space, okay? So, this common multiple, so we have here 16.58 F. Okay, 16.58 F. So, let's try to find it out. So, let's have this one, 16.58 is equal to, okay, is equal to F plus, alright, so plus, so this will become, okay, so 16.58 over 12.89. So that will be 1.286. Negative 1.286 F. Alright, so this will eventually become negative. Alright, so this will eventually become negative. So 16.58. Okay, so 1 minus 1.286. So that will be negative 0.286 F. Okay, so to get the final answer, so the F should be negative 16.58 over 0.286. Either 286. So the answer will be negative 57.97 centimeter. So that is the focal length of your convex mirror. Alright, so the focal length of this is the complete answer. The focal length of the convex mirror is negative 57.97 centimeter. That was a large mirror. Okay, so that is a large mirror. So no wonder it has the same answer. Now, let's check our work. Now, if it is a convex mirror, based on the sign convention that we had earlier, it should be negative. So therefore, our answer is negative. The given was convex mirror, then therefore this is correct. Okay, so based on the sign convention. Okay, that was the second sample problem. Let's go to the next one. Alright, so a concave mirror produces an inverted image that is magnified 2.5-fold. Determine the image distance if the original object was placed 4.0 centimeter in front of the mirror. Okay, so what do we have right here? Okay, first one, inverted image. The second is the concave mirror. Alright? So we should take note of this thing that we have right here. This one and this one. And the image was magnified. What do you mean by 2.5-fold? What do you mean by 2.5-fold? So it means that if we write it right here on our data, it means that that is 2.5x. Alright, so that was 2.5x. Okay, so next one, we have the original object. So that is the distance of the object should be 4.0 centimeter. So we don't have any problem with this one. So we are asked to find out the image distance. Now, let's check the data if they are all correct. Okay, so since that is an inverted image, so this 2.5 that we have right here, this 2.5 should be negative because that is an inverted image. Okay, remember, negative. Okay, so inverted image will produce a negative magnification. Okay, so we have it right here. So negative. Okay, so how about the distance of the object? So we don't have any problem on this because it is just always positive. Okay, now with this case, so we don't have focal length. So in this case, we will going to use the second equation, which is h sub I, or height of image divided by height of the object, is equal to negative v sub I over distance of the object. Now, since we don't have any height over here, so we can cancel this one. Okay, so we can use negative d sub I over d sub O. Okay, so let's rearrange the formula over here. So to get the d sub I, so negative d sub I, then we have m d sub O. Okay, so let's substitute the value. So we have negative 2.5 x. All right, 2.5 times 4.0 cm. Okay, so cancel the negative, and the answer should be, okay, so 2.5 times 4.0, so 2.5 times 4, that will be 10 cm. Alright, so the distance of the image is 10 centimeter. That is the complete answer. Okay, so 10 cm. So let's try to analyze this one. If this is a real image based on its answer, which is positive. Okay, so we have here the positive. Okay, so if this is the real image, does it follows the problem? Yes. Real image yields inverted image. Alright, so it means that they are, the answer that we got right here is correct. Okay, so that is for the second problem. Okay, so this is the first, that is the third problem. Okay, so next, problem number 4. Okay, so we have it, we have right here the problem number 4, so which is completely different, I think. Okay, so again, you can pause this video to answer it beforehand. Okay, so determine the image height for a 5.0 centimeter tall object. Place 45 centimeter from a concave mirror. If the image is real and is 22.5 centimeter from the mirror, what is the image height? Okay, so first thing to do, find the things that we need before getting the data. So the problem uses concave mirror and the image that was produced is real. Okay, so concave mirror, real. So number 1, number 2. Okay, so we can now write the data. Okay, so first one, this one is the height of the object. So we don't have any problem with the height of the object. It is always positive. All right, next one. This 45 centimeter. All right, this 45 centimeter is the distance of the object. So therefore, that is 4500 cm. Okay, next one. The image is real, and this is the distance of the image. That's 22.5 cm. Then we are looking for the height of the image. All right, so what is the height of the image? Now, let's check our data if that is good already. So, since that is a real image, then therefore the distance of the image is positive. So, this one is good. Correct, correct. So, we can now solve for the problem. Now, since this problem doesn't have focal length, since this problem doesn't have any focal length at all, we can use the magnification equation, the second equation, which is height of the image divided by height of the object is equal to negative d sub I over distance of the object. Alright, since we don't have magnification over here, we don't need the magnification, we can cancel this one. Okay, so therefore, we are left behind with this equation. So we will arrange this equation. We can rearrange this equation to find what we are looking for. So we can arrange this one as h sub I is equal to height of the object multiplied by the distance of the image, negative, over distance of the object. Okay, so there you go. Now let's plug those values. So we have 5.0. Next, the distance of the image is 22.5. And don't forget the negative. Alright, so the negative sign. Okay, so again, I will rewrite this one once again. Okay, so the negative sign, then we have the 22.5. There you go. Okay, so next one, 45. Okay. Okay, so there you go. Now, let's solve 5 times 22.5. That will be negative 112.5 over 45. So, what will be the height of the image? 112.5 over 45. So, the answer is negative okay, negative 2.5 cm. Negative. Right, so negative sign. Okay, so what do we mean by the negative sign on our answer? What do we mean by this negative sign that we have right here? The negative sign that you have right here means that the image is inverted. Okay, based on our sign convention. Now, if it is inverted, does it follows the data on the problem? Does it follows what the problem says? Yes, of course. Alright, so it follows the problem's real image. Alright, so the real image that you have right here. So, therefore, our answer is correct. Okay, so that is 2.5 centimeter. Okay, so that was the fourth problem. Okay, so this will be the last problem for the mirror equation that we have right here. So, determine the image distance and image height for a 5 centimeter tall object placed 30 centimeter from a concave mirror having a focal length of 15 centimeters. Okay, so how do we approach this one? So, the same thing. Okay, so the problem uses concave mirror. Okay, so nothing else. Okay, so it doesn't say if it is a real image or it doesn't say if it is a real image or even a virtual image. So it doesn't say anything like that. So only the concave mirror, only this one. Okay, so let's write everything. Okay, so this will be the height of the object. So again, we don't have any problems on that because that is always positive. Next one, what do we have right here? So we have the distance of the object. Okay, so 30.00 cm. Again, that is always positive. Distance of the object. Next one, how about the focal length? Okay, since it is a concave mirror, so this 15 centimeter that you have right here is a positive one. Right, so that is a positive 15 centimeter. So it's not a negative because that is a concave mirror. This one is a concave mirror. So, we are asked to find out, which is the image distance. Ano yung image distance and ano yung height ng image. Alright, so what is the height of the image? Okay, so that is the height of the image. So, I think we are good and ready to go. So, everything is correct and checked. Okay, so there are two things that we need to do here. First one, we will use, okay, in order to compute the d sub I, so in order to compute the d sub I, we will use this formula. Alright, so let's use this formula first. So, let's go. Let's substitute everything. So, we have the focal length is 1 over 15 is equal to 1 over 30. Okay, and plus 1 over d sub I. Then, let's use the least common multiple. So, 30 d sub I. So, therefore, so we have 2 over here plus, equal. Alright, equals d sub I plus 30. Okay, so there you go. Then upon doing it, upon using algebra on the process, we can get the d sub I is 30. Okay, so d sub I is 30 centimeters. Okay, so that is the d sub I. So we have now an answer on the distance of the image. Now, if we have an answer on the distance of the image, then we can use this formula. Okay, height of the image over height of the object is equal to negative d sub I over d sub O. So we can now use this one. So since we don't need the magnification, we can cancel this one out. Okay, so we don't need the magnification here. So substitute the... Okay, so we are looking for the height of the image. So the formula should be height of the image is equal to height of the object d sub I over d sub O. Okay, so let's substitute everything. So height of the object was 5 cm. And the d sub I is negative, then that is 30 over d sub O, which is also 30. Okay, so what will be the height of the image? So cancel. Alright, so cancel that one out. So the answer should be negative 5.00 cm. So that was your height of the image. Alright? Okay, so let's analyze this one. Since this is the last problem for the mirror equation, so let's analyze this one. Now, what is the lost? Okay, what is the lost? So I'll put the T here. Alright, so we all know that the distance of the image is positive, so therefore that is a real image. Then, the height of the image is negative, then therefore that is an inverted one. Okay, inverted image. Now, what about the size of the object? Or size of the image, rather. Okay, what about the size of the image? Now, as you can see, the image is 5.00 cm. The height of the object was 5.00 cm. So, therefore, it has the same size. Alright, so it has the same size. Now, what about the lost? Okay, what about the lost? So, the object, okay, so if the focal length is 15 centimeter, then therefore, the center of curvature, 15 times 2 is 30 centimeter. So, therefore, the object is placed at C. Okay, the object is placed at C. So, therefore, the image is formed at C. Alright, so the image is formed at C as well. Okay, so that is the analysis for this problem that we have right here. Alright, so that was for the mirror equation. So let's go now to the next part, which is the lens equation. So, oh, I forgot there is a... Okay, before we go to the lens equation, there's a last problem. Okay, so there's a last problem for our mirror equation. So let's try to do this one. Again, you can pause the video. Alright, so you can pause the video if you want. So before you can answer this one beforehand. Okay? So, what was the problem? Determine the magnification of the image for an object placed 12.25 cm from a convex mirror, having a focal length of 6.38 centimeters. Okay, so let's try to find out first what kind of mirror the problem used. Okay, so the mirror or the mirror that was used in this problem is a convex mirror, like so, over here. Okay, so that was a convex mirror. And everything, okay, there's nothing else given aside from this mirror that we have right here. So let's write now the data. So let's start first with the thing that we have right here. So what is this? Okay, so this is the distance of the object. That was 12.25 cm. Next one, how about the focal length? Alright, so how about the focal length? So the focal length is 6.38 cm. And we are looking for the magnification. Alright, so we are looking for the magnification. But before you look for the magnification, we should look first for the distance of the image. Alright, so we are looking for these two entities that we have right here. Now, before we go to problem solving, let's check first if we have the correct data. So since this is a convex mirror, so we all know that the focal length of the convex mirror is negative. Alright, based on the sign convention. So it is always negative. So we have it right here. So the distance of the object, so no problem. No problem with this one. So we are now good and ready to go. Okay, so we will use the 1 over f, 1 over d sub o, plus 1 over d sub I. Okay, so if I do, I die. Alright, so 1 over f is negative 6.38 is equal to 1 over 12.25 plus 1 over d sub I. So we need to find the d sub I in order for us to use this formula. Alright, so in order for us to use this formula, we need to get the d sub I. Alright, so let's use now the least common multiple. Alright, so we have 12.25 d sub I. Okay, so let's start first with the first term, which is 12.25 over 6.38. That will be negative 1920. Alright, so that will be d sub I. Next is equal to d sub I plus 12.25. There you go. Okay, so let's do a bit of algebra here. Transpose it over there. So the d sub I will be 1 plus 1 minus 1.920. 1 minus 1.920. So the answer will be, alright, so the answer, or rather negative 1. Negative 1 minus 1.920. So the answer will be negative 2.92 d sub I. Is equal to 12.25. So what will be the d sub I that we have right here? So the d sub I should be 12.25 over 2.92. Right, so the answer will be 4.19. So the answer will be 4.2. Alright, so 4.20 cm. Alright, so 4.20 cm, that will be our d sub I. Don't forget the negative. So it means that this is a virtual image. Alright, so this is a virtual image. Okay, produced by this convex mirror. Now, what is the magnification? Now, with the use of this formula, we can find the magnification. So, let's plug those values. Okay, so I will solve it somewhere here. Alright, so we have negative 4.20. Alright, so times the negative sign there. And we have the d sub o, which is 12.25. So 4.20 over 12.25. So the image is, all right, so the magnification is, since it will cancel all the negative, so it will cancel all the negative, so the answer is 0.34x. Okay, so the answer is 0.34x. So what does this one means? It means that the image is virtual and upright. Alright, so the image is virtual and upright because positive, the magnification is in positive value. Okay, so that was, this is the last problem for the mirror equation. Now, let's go now to the lens equation. Now, for this one, I will change the color of my pen to orange. Alright, so we talked about earlier that ray tracing is very useful. Yes, that is very useful, but kind of tedious in terms of how it's done. And in terms of accuracy, it requires precise drawings. So you need to have a straight line, a good measuring equipment like a very straight ruler, alright, so on and then so forth. So therefore, we will going to use the lens equation. Now, however, it will require some algebra. Okay, now what is this lens equation? So we can verify the result that we have right here using a ray diagram. Okay, in our previous video, alright, so in our previous video, so we can use this ray diagram to somehow predict the characteristic of the image that we have right here. So there you go. Okay, it is inverted. Okay, so in this case, what is the lens equation? Now, if you're going to use, so guys, if you will going to use the same method that we use to derive the mirror equation by the use of the similar triangles, okay? So if you use the similar triangle method in deriving the mirror equation, then it will work as well on the lens equation since they have the same parameters. Okay? The lens and the mirror has the same parameters. Okay? And both of them follows the similar triangle concept. Okay? So therefore, if you derive this one using that concept, you will end up, alright, so you will end up with the same formula. Like the one that you have right here. Okay? So you will end up with the same formula based on that derivation. And based on the concept of the similar triangles. Okay? So not only the mirror equation, or not only this equation, which is similar, but also with the magnification. As I've said earlier, they have the same parameters. They have the same parameters, so therefore, there will be no reason why they will not have the same equations. Okay, so including the magnification equation, they are also the same. Okay, so therefore, we can now proceed with the convention. Alright, so what are the conventions? Actually, they are the same. In terms of the distance of the object, always positive. The distance of the image is the same thing. Okay, height of the object, it's the same thing. Height of the image, upright, positive, inverted, negative. Magnification, positive magnification is upright, virtual. Negative magnification is inverted, real. Alright, so positive and negative magnification. Now, the only difference is this one. Alright, for the converging lens or so-called convex lens, for the converging lens, that is positive. Okay, that will be positive. So, for the concave lens or diverging lens, it is negative. Okay, it is negative. Okay, so just take note of this one. Alright, so just take note of this one. So, let's go now to the sample problems. Okay, so there you have it. Okay, so sample problem number 1. Okay, so a pen is in front of a converging lens which has a focal length of 17.3 centimeter. Now, the real image is formed or located at 19.62 centimeter from the lens. Determine the distance of the original object from the lens. Alright, now, the question is, do they have the same pattern? All right, do they have the same method, the way we solve the mirror equation? The answer is yes. Okay, they have the same pattern. Okay, so you can pause the video. You can answer this one beforehand. Okay, so first thing to do is to find out what is the mirror or what is the lens. This time we are going to use a lens. So the lens that they use is converging lens. And also, in the problem, there is a clue, which is the real image was produced. Alright, so the image was produced. So we are asked to find out the original distance of the object. Alright, so the original object's distance. Okay, so that was the task here. Okay, so with that, we identified already what kind of lens and what kind of image that is formed. Then therefore, we can now write the data. So the focal length was 17.3 centimeter. All right, next one is the real image. So this will be the distance of the image. So that was 19.62 cm. And finally, we are looking for the distance of the object. Now, let's check first if we have the right sign convention. So for the focal length, okay, based on this convention, converging lens have positive focal length. So therefore, we are good here. Now, distance of the image. So this is a real image. So the real image has positive value. So this is a positive, so this is good. Okay, so we were going to use the same formula that we had earlier. So distance of the object plus distance of the image. Now we can now plug this one. So 1 over 17.3 is equal to 1 over 19.62 plus 1 over d sub O. There you go. Okay, so we will use 19.62 d sub O as least common multiple. And let's try to find it out. So 19.62 over 17.3. So that will be 1.134 d sub O. Right. It's equal to d sub O plus 19.62. So there you go. So transpose this one over here. So minus 1 plus 1.134. So that will be 0.134 d sub O. Not positive, not negative. Is equal to 19.62. Then therefore, our d sub O should be 19.62 over 134. So, 19.62 over 0.134. So the answer should be 146. All right, so not 146.42 centimeter. That is the distance of the object. All right, so that was the distance of the object. So meaning to say this is beyond C. Okay, so this is beyond C. Okay, as we assumed based on the answer that you have over here. Okay, so there's no problem with the... Okay, so I'm just double checking everything. Okay, so this is the answer that we have over here. Okay, 19.62. Okay, so no problem with our answer. Okay, so that is for the first problem. Okay, so did we have the same answer? Okay, so please write your comment in the comment section of this video if you have the right, if you have the same answer. Okay, so if you got the right answer for this question. Okay, let's go now to the second problem. Okay, a ring is placed a distance of 3.9 centimeter from a converging lens. The virtual image was located 24.56 cm off from the lens. What is the focal length of this lens? Okay, so first thing to do is to find out what kind of mirror and what kind of image that was in the problem. Okay, so we have here the converging lens. Okay, so take note of that. And also we have the virtual image. Okay, so we are asked to find out what is the focal length. Okay, we are asked to find out what is the focal length. So we can now write all the data. Okay, so this is the object distance, I presume. Okay, so distance of the object is equal to 3.9 cm. Next one, how about the virtual image? So this is the distance of the image, which is 24.56 cm. Next, the focal length, which is missing. Alright, so let's check everything. So the distance of the object is always positive, so we can leave that one. Okay, how about the distance of the image? So we have the virtual image over here, so we can say that the image is negative. Okay, so the distance of the image over here on our data is negative because that is a virtual image based on the sign convention. So if we're going back on that one, so this is the one that we are talking about. Okay, there you go. Now again, we were going to use the same formula. D sub O plus D sub I. Then let's substitute. 1 over F is equal to 1 over 3.9 plus 1 over negative 24.56. Alright, so therefore, we will going to use the negative 24.56 as our least common denominator or least common multiple. So let's go now with our process here. So okay, in this case, cancel the F. Alright, so cancel F. So we have negative 24.56 is equal to okay, so 24.56 24 okay, 56 over 3.9. Okay, so that was negative. Right, so that was negative 6.29. That was negative 6.297. All right, F. And lastly, we have cancel. So we have plus F. Okay, so let's try to find out what is this. So negative 24.56. Then this one. So negative 6.297 plus 1. So that will be minus 5.297. All right, so that was 5.297. Then that is F over here. Okay. So let me double check if I got the right thing. Okay, D sub I, converging lens. Okay, so there you go. Okay, so they are all correct. So the focal length that we should get right here is 24.56 over 5.297. So cancel all the negatives. As we expect, we have a positive answer of 4.64 centimeter. So that was our focal length, 4.64 centimeters. So therefore, positive. This is positive. It's because of this. Okay? Now, if you're going to take a look, a positive focal length is a convex lens or converging lens. Alright, so our answer here is correct. Okay, so our answer here is correct. Alright, so let's go now to the third problem. Alright, so the third problem was all about, okay, so determine the image distance and image height for a 16.3 centimeter tall object. Place 24 centimeter from a converging lens having a focal length of 12 cm. Okay, so having a focal length of 12 cm. So, again, you can pause this video if you want to answer this one beforehand. Okay, so let's take a look. Okay, so the mirror or the lens that was used is a converging lens. And there's no such thing as virtual or real images that was stated here. Okay, so let's go now write the data. Okay, Okay, so we have here the image, the height of the object. So that is 16.3 centimeter. And 24 here is the distance of the object. 24 centimeter. Next one. We have the focal length for this one. So focal length is 12 cm. Now we are asked to find out the image distance and also the height of the image. So both of them are missing here. Now let's check this one if we are good to go. Okay, so this one, the height of the object and distance of the object, they are always positive. Next one, how about the focal length? So since this is a converging lens, the focal length is positive 12. Alright, so the focal length is positive 12, so this is good. Okay, so now we will divide this one into two processes. So the first process is to compute for the d sub I. Alright, so to compute for the d sub I, so we have 1 over f, 1 over d sub o, plus 1 over d sub I. So substitute, so 1 over 12 is equal to 1 over 24 plus 1 over d sub I. So 24 d sub I, then this will become 2 d sub I is equal to d sub I plus 24. Okay, there you go. So the answer is d sub I is equal to 24. Alright, so probably the object was placed in the C. Okay, the object was at C. Okay, so the object, this object. Alright, so at C. Okay, so 24 centimeter. There you have it. Now, let's go now to the height of the image. Now, to compute for the height of the image, we will going to use this equation. Minus d sub I over d sub O. Alright, so we will use this equation. So, since we don't need this one, so height of the image is equal to height of the object multiplied by the distance of the image over d sub O. Alright, so what is the height of the object? Okay, so the height of the object is 16.3 times negative d sub I is 24. There you go. And we have the d sub O of 24. Okay, so the height of the image is, alright, so the height of the image is, cancel this one. Alright, so the height of the image is cancelled. So the height of the image is negative 16.3 centimeters. Okay, so we can say that the height of the image is the same size as the object. Same size as the object. Okay, because we have computed this value that we have right here, 16.3. Okay, so that was problem number 3. Okay, so we'll go now to the fourth and last problem for the lens equation. Let's go. Okay, so this is the fourth and last problem that we have right here. So again, you can pause this video if you want to answer this one beforehand. Okay, so determine the magnification of the image for an object placed 6.39 centimeter from a diverging lens having a focal length of 18.6 centimeters. Okay, having a focal length of 18.6 centimeters. So let's take a look at the problem. So the problem is using the diverging lens. Okay, so I think nothing else. Alright, so we don't have a type of image, only a type of lens. Okay, so let's write now everything. So what was this one? So place the image for an object placed. So meaning to say this is the distance of the object at 6.39 cm. Alright, next one. The focal length is 18.6 centimeter. Alright, so we are looking for the magnification. Now, we cannot find the magnification if we don't have d sub I. Okay, so we will find these two all together. So before we go to the problem solving process, check first if we have the same, the correct sign convention. The d sub O, okay, so always positive. Next one, how about the focal length? All right, so since this is a diverging lens, the focal length should be negative 18.6. All right, so the focal length is negative 18.6 because that is a diverging lens based on the sign convention. So if we will go back there, so this is what I am talking about. Okay, so that was negative. All right, so with that, we are now good and ready to go. So first one is we will going to use this equation, d sub o plus d sub I. Therefore, 1 over negative 18.6 is equal to 1 over 6.39 plus the d sub I, which is said to be missing. Okay, so we have negative 18.6 d sub I. So we have here negative. So okay, so negative tapos negative here. So we have here the d sub I. Okay. So it's equal to, okay, so 18.6. 18.6 over 6.39. So that was negative 2.910. 2.991 rather. Alright. So d sub I. Plus negative 18.6. Okay. So there you have it. So we will transpose this one. Alright. So we will transpose this one on the other side. So the d sub I should be 2.911 plus 1, so that will be 3.911. Okay, positive. And we have here the negative 18.6. So the d sub I, all right, so the d sub I for this problem is, even though we are not looking for the d sub I, even though we are not looking for the distance of the image, so therefore the answer here should be 18.6 over 3.911. So the answer is 4.76. Okay, so 4.76 centimeters. That was the distance of the image. Alright, so is it negative or positive? So we have here the negative, so it will be carried out here. So what does the negative d sub I means? Alright, so what does the negative d sub I means? It means this is virtual. Alright, so it means that is virtual. Now, let's take a look at the magnification. Now, to get the magnification, since we have now the d sub I, we can now use this formula, d sub I over d sub O. So, let's substitute the things that we have right here, negative, then negative 4.76 over the d sub O of 6.39. So, therefore, the magnification for this problem, cancel all the negatives, 4.76 over 6.39. So the answer is 0.74x. So what does the magnification means? It is a positive, so therefore it is upright. Alright, so it is upright. Upright, then 0.74 reduced. Alright, so reduced. Okay, so virtual, upright, and reduced. So, what is the location of the image? Okay, to complete the laws that we have right here, what is the location of this image? Behind the lens. Okay, so that is behind the lens. That is the location for our image that we have right here. Now, this is the fourth and last problem for the lens equation. So, that is reduced. Okay, you can see it. All right, so what is the purpose? Okay, what is the application of this one? Now, if you happen to go to a department store and look for reading glasses, if you happen to go on a department store and look for these reading glasses, you will notice some numbers on your reading glasses, like the one that you have right here. Now, this one, that is positive because that is for far-sighted person. The negative ones are for the nearsighted people. All right. So the positive that you have right here, this is the magnification. Alright, so this is the magnification power of your reading glass that you have right here, positive. So it means that it will make the image larger. It will make the image larger. So that is why higher magnification rate, like the one that you have right here, the higher the magnification rate, the more, the larger the image that it will form. So this is good for people who cannot read, okay, a small image coming from a book, something like that. So this magnification is good for that one. Okay, so that is for the reading glasses. So the numbers that you found on your reading glass is the magnification power of that glasses. Okay, to sum it all up, so the mirror equation that we used in our video lesson for this episode. Okay, so as you all know, the ray diagram is very limited. So we use these equations that we have over here, the mirror formula and the magnification formula. Okay, and for the lens equation, well, basically it's the same thing. We have the the lens formula and the magnification formula. Okay, in order to solve word problems related to lens equation. Okay, so with that, all right, so that ends up our episode today. So it is a very lengthy episode. All right, so I hope you'll be able to get all the concepts and the step-by-step process in solving problems related to spherical mirrors and lenses alike. Okay, so with the use of those equations that you will have right there will be no problem. I am very confident enough that you will solve any mirror and lens equation problems that you will encounter. All right, so if you value this lesson or if you value this video lesson enough, you can leave a like on the, okay, you can leave a thumbs up on the description of this video below. All right, and you can subscribe to my channel for more video lessons like the one that we have right here in the future. All right, so if you have suggestion and comments, you can write it down in the comment section of this video. Okay, so with that ends up our video lesson for today. And let's see each other next time, guys. Stay safe. All right, stay safe and peace out, everyone. Peace out. Peace out.
子供なのね夢を追って傷ついて嘘が下手なくせ